Okay, we're ready to rock and roll on our fourth and then final free response question for winter break. And we've got quite a doozy. Out of the four, I think this is the most challenging one. And perhaps one of the biggest challenges is just to find the most efficient way to solve each of these problems, especially part B and C, and not get trapped into some longer solutions that all of a sudden, before you know it, you spend 20 minutes on one problem and it really takes away from the other problems on the test. So they gave us kind of a weird function. They said instead of saying like y equals x squared or y equals x cubed, they just said y equals x to the n, where n's anything greater than 1. So do think of functions like y equals x squared or y equals x cubed or y equals x to the fourth. And what they all have in common is that they do go through the point 1 comma 1 because 1 raised to any power is equal to 1. Notice, as the exponent does get bigger, maybe the curve bends more, but this kind of has the same general behavior in passing through the point 1, 1. Part A is extremely straightforward, and the only thing that could possibly throw us off is if we're slightly uncomfortable with doing things in terms of n. And so what I'm going to do is I'm going to go ahead and find the antiderivative. We're going to add 1 to that exponent and then multiply by the reciprocal of the new exponent. Of course, you could have written x to the n plus 1 divided by n plus 1. That would also have been equivalent. And then I've got bounds of 0 and 1. Notice the bounds, because the integral is with respect to x, you instantly know that the variable here in play is x. So we're going to substitute the 1 in for x. And I got 1 over n plus 1 minus, we'll substitute the 0, and I just got 0. So my final answer was 1 over n plus 1. And that, for me, was the integral from 0 to 1. Now, keep in mind, this also represents the area underneath that entire curve, which is going to come into play here shortly. So part B, we're going to try to find the area of this triangular region right here. And the moment they said that, I said, there's really two ways we could go about this. We could kind of stick to our non-calculus techniques and just rely on the area of a triangle is going to be 1/2 times his base times his height. Or we could kind of take a calculus approach and do an integral of line L. Now the tricky thing here is we have to get that x-intercept. If that x-intercept was called alpha A, we could integrate from A to 1, and then we would just be integrating the equation of this tangent line and so forth. But again, I'm going to end it up, after I kind of considered both options, I ended up going with the non-calculus technique. I thought that was going to be a little more direct, but either one you choose, you're going to have to go find that x-intercept. And just kind of backtracking, we can't find this x-intercept right here until you first write the equation of that tangent line. So I said, well, let's see, the curve's derivative is going to be nx to the n minus 1. If you evaluate that derivative at 1, you will get a slope of n. So I said that the tangent line was y minus 1 equals n quantity x minus 1. Okay, so that's the equation of my tangent line right here. Now what I'm going to try to do is I'm going to try to find the x-intercept of that tangent line. And if I want the x-intercept, that means I'm going to have to substitute a 0 in for y. So let's see what that gives me. Negative 1 equals n times x minus n. If I distribute the n, add the n over, and then divide by n. So I'm going to say n minus 1 all over n is the x-intercept that corresponds, let's see here, it corresponds to this point right there. All right. So now the question becomes, how big is the base of this triangle? I want this section right here. Keep in mind, the x-intercept we just found measures the distance from the origin up to point A. So that distance right there is the n minus 1 over n. So in order to get the red distance, I'm going to do 1 minus the x-intercept. So here we go. We've got the area is 1/2. The base is going to be 1 minus n minus 1 over n. And then the height of this triangle right here is simply 1. So that kind of worked out nice. Now, as far as cleaning up this base right here, you could try to create common denominators and turn them into one fraction. I'm going to take the opposite approach, and I'm going to decompose this one right here, make like a beaver and split it up. So I'm going to have 1 minus the quantity 1 minus 1 over n. I thought that was the easiest approach. And then as you distribute the negative, we're going to get the 1's to cancel, and you get a positive 1 over n. And so you get a final area of 1 over 2n, which does confirm their answer here. And again, this was one of those neat problems where they kind of told you what the answer was supposed to be. They said show that the area is 1 over 2n, and so we've just confirmed that answer. Now, part C, here comes the real interesting one where efficiency becomes a real prized commodity here. As far as finding the area of S, let me first of all, maybe some of you were tempted to go about this way. Maybe you split the region into two sections and you did two integrals, one from 0 to alpha A, and then another one from alpha A to 1 where you did upper minus lower. I'm going to really encourage you to stay away from that technique. Besides being very challenging, it's also very time consuming. And what I want you to do is I want you to say, okay, in part A, we found all the area underneath the curve, right? And we said everything underneath the curve had an area of 1 over n plus 1. And then in part B, you found the area of the triangular region, right? And we said the area of that triangular region was 1 over 2n. Well, guess what? If we subtract those two rascals, we're going to end up with the area that they're asking for. That's going to give us the area of region S right here. So that's what all we're going to do is we're going to say the area of region S is the red one minus the blue one. And that's all it is for the first half of part C. Now, besides finding the area of S, they also wanted me to now find the value of n that maximizes the area of S. And so what we're going to do, anytime you want to maximize or minimize some quantity, we're going to take the derivative, set it equal to 0, and then of course we'll try to confirm that it's a maximum value instead of a minimum. So what we're going to do here is we're going to find our derivative. I'm really visualizing, for this term right here, I'm visualizing n plus 1 to the negative 1 power. So the derivative of negative 1, n plus 1 to the negative 2, derivative of the inside is just a 1. The good news is n's really a variable here because n's are independent variable on this expression. And then over here for this term, I'm visualizing negative 1 half n to the negative 1 power is what I'm seeing. So I got positive 1 half n to the negative 2. Let's see if we can clean this derivative up just a little bit. So our derivative is negative 1 over n plus 1 quantity squared plus 1 over 2n squared. We're going to set it equal to 0. I've got 1 over 2n squared equals 1 over n plus 1 quantity squared. Just a lot of old-fashioned algebra right now. We could cross multiply, or we could just say we're going to reciprocate both sides because there's only one fraction on each side. You know, really no calculus left in the problem from here on out. Just a whole lot of, feels like we've been transported back to Algebra 2 trig here. So let's see, if I subtract that over, I get 1n squared minus 2n minus 1. Doesn't factor. So let's say the quadratic formula says that n should equal negative b plus or minus the square root of b squared minus 4ac all over 2 times a. N's really 2 plus or minus radical 8 over 2. And at this moment, you're probably wondering, am I doing this right? I mean, I don't normally do this kind of work on a calculus problem, but sure enough, this is the best way to do it. Now, as you get these two solutions that we have here, remember the domain. They said the domain was n had to be greater than 1, so what we're going to do is we're going to reject the 1 minus radical 2 solution, and so we're going to say n equals 1 plus radical 2 is our solution. That's the value of n that hopefully maximizes this area of region S. My number line is going to start at 1. I'm going to say 1 plus radical 2 is my critical point. And what we've got here is you're trying to think of a number that falls in that first interval. Surely 2 does squeeze in there. So I'm going to substitute a 2 into my a prime expression, and I did get a positive value. And then I substituted a 3, and I got a negative value. So we have just proven that 1 plus radical 2 does maximize the area of region S.